All right, today we're jumping into one of the most elegant and honestly powerful ideas in all of physics. It's a concept that can take what looks like a total nightmare of a problem and turn it into something you can solve on the back of a napkin. Let's dive in.
So, let's start with a really fundamental question. You've got these invisible forces all around us, like the electric field that surrounds every charged particle. But how in the world did scientists actually sit down and calculate how strong that force is at any given point?
Well, the most direct way, what you might call the brute force method, is usually just incredibly difficult. Imagine you want to find the electric field coming from a charged wire that's infinitely long. To do that, you'd have to add up the tiny little push from every single piece of that wire, which means you're going to have to do some nasty calculus.
And the steps involved are, well, they're a lot. You have to take one tiny slice of the wire, find the tiny field it creates, then figure out which parts of that field are going to get canceled out by all the other pieces. And then you have to add up all those remaining little bits from negative infinity all the way to positive infinity. It is a true mathematical marathon.
And after you go through all of that pain, the answer you get is kinda weird. You see, we all learned that the force from a single charge drops off with the square of the distance. But for an infinite line, it only drops off proportional to the distance. It's a totally different relationship, and it took all that heavy lifting to figure it out.
Now, this is exactly the kind of problem that makes a physicist stop and think, wait a minute, there has to be a better way. And guess what? There is. The secret, the real clue, is to completely change how we visualize the problem in the first place.
So instead of just thinking in terms of equations, physicists came up with this brilliant visual tool, electric field lines. Think of them like a weather map for an invisible force. The lines themselves point in the direction the force would push. And, this is the crucial part, how close together the lines are tells you how strong the field is. If the lines are packed tightly, you've got a strong field. If they're spread out, it's weaker. There's even a rule about how many lines a certain amount of charge creates.
Okay, so this visual map leads to a totally different kind of question, a really powerful one. What if, instead of doing all that crazy calculus to find the field strength at one specific point, what if we just drew an imaginary bubble around some charges and simply counted the total number of field lines poking through the surface of that bubble? This idea of counting lines has a name, of course. It's called electric flux. But the concept is dead simple. You picture the field lines flowing outwards. You draw any imaginary closed shape you want. It could be a perfect sphere, a box, even a lumpy potato shape. It doesn't matter. And you just count the net number of lines poking out of it. That final count, that's your electric flux. So we have this really hard problem on one hand, and this new kind of strange idea about just counting lines on the other. Now, let's put them together for the big reveal. This is the physicist's ultimate shortcut. And this is it. This is Gauss's law. What it says is that the total number of field lines poking out of any closed surface you can imagine is directly proportional to the total amount of charge that's trapped inside that surface. That's it. It's so simple it's almost hard to believe, but it is unbelievably profound.
The really crucial idea here is that Gauss's law creates this amazing, direct link between the source of the field, the charge tucked away inside, and the overall pattern of the field on the outside. It's a deep statement about the fundamental geometry of how fields work in our universe.
And the logic for why it works is just beautiful. Think about it. If you have a charge inside your imaginary bubble, its field lines have to pass through the surface to get out, right? So they add to your count. But what if the charge is outside the bubble? Well, any field line that goes into the bubble on one side must also come back out on the other side. The net change to your count is exactly zero. It's brilliant. Only the charge you've actually enclosed matters.
Okay, so the theory sounds cool, but let's see the payoff. Let's go back to one of those famously impossible problems and watch how Gauss's law absolutely demolishes it.
This right here is a monster of a problem, calculating the electric field outside a solid sphere of charge. The gravitational version of this, by the way, famously took Sir Isaac Newton himself years to prove, and he had to invent calculus to do it. It's a beast that requires you to add up the effects from every tiny speck of charge inside.
And this slide just says it all, doesn't it? On the left, the brute force method, a three-dimensional integral from hell, a total mathematical nightmare. And on the right, the Gauss's law method. Step 1, draw a bigger imaginary sphere around the charged one. Step 2, apply one simple equation.
The elegance is just staggering.
So here's the magic trick. Why does this work so perfectly for a sphere? One word, symmetry. Because a sphere is perfectly symmetrical, we know without a doubt that the electric field must have the exact same strength at every single point on our imaginary outer surface. And because of that perfect symmetry, all that scary calculus just collapses into simple multiplication. The field strength E times the surface area of our sphere. You do one little step of algebra, and boom, there's your answer. The electric field E equals the total charge Q divided by 4 pi epsilon naught r squared. Now, does that equation look familiar to you? It really, really should. Because that is the exact same formula for the field of a single tiny point charge. This is the incredible result, the thing that took Newton years to prove. Gauss's law shows us, in just a couple of simple steps, that from the outside, a whole sphere of charge acts exactly as if all that charge were squeezed down into one tiny little point right at its center. Just incredible.
So this is clearly more than just a neat trick for solving physics problems. What's the bigger picture here? What's the real takeaway? Well, Gauss's law is basically the ultimate example of working smarter, not harder. In any situation with symmetry, it transforms a terrifying calculus problem into simple algebra. On a deeper level, it reveals this fundamental connection between the sources of a field and the field's actual structure in space. But maybe the biggest lesson of all is this. Sometimes, the hardest problems become simple if you can just find the right way to look at them.
And that really leaves us with a final thought, doesn't it? Gauss's law isn't just about physics. It's a lesson in problem solving. It makes you wonder, what other seemingly impossible problems, maybe in science, maybe in our own lives, are just waiting for us to find that one elegant shift in perspective that makes everything suddenly clear?